Yesterday, we found out that the ball that we dropped had 2.1 joules of potential energy at the top. Today, we want to try to find out how much kinetic energy it has right before it hit the floor. So, to talk about kinetic energy, same thing. This comes from kinematics again, the idea that work is force times distance. After doing some math, we find out that the kinetic energy is 1/2 mv squared. And Sheeny had talked about this earlier in the week in her video about kinetic energy and potential energy. So we need to know this. The law of conservation of energy says that energy cannot be created, nor can it be destroyed. It can only be transferred from one type of energy to another type. So when it has potential energy at the top, when it gets to the floor, it has lost all of its potential energy. That has been changed into kinetic energy. And so we find out that at the bottom, the kinetic energy equals whatever amount of potential energy that had at the top. And we found out the other day that that is 2.1 joules. Today we want to try to find out how much velocity it has. How fast is it moving right when it hits the floor? And we'll do that a couple different ways. So number one, let's look at this. This idea that potential energy equals kinetic. Potential energy at the top equals kinetic energy at the bottom. As we know from the other day, potential energy is mass times gravity times height. Kinetic energy is 1/2 mv squared. And you'll notice there's a mass on both sides of the equation. So that actually cancels out and we don't need it in the next line. After a little bit of algebra, we just multiply both sides by 2, take the square root of both sides. We find out that the velocity is the square root of 2gh. Now, let's go ahead and use that to calculate how fast was the ball going right before it hit the floor. According to the law of conservation of energy, when we plug in these numbers, if you recall, the height that I dropped it from was 7 feet, which is 2.1 meters. And we end up with a velocity of 6.4 meters per second. Now, let's go ahead and calculate that using a different method to see if we get the same answer. We're going to go back to some kinematics. So if you would, let's measure how long it takes the ball to fall to the floor. Now, I did that using my video, and you could do the same thing. If you took video, you can count frames. You probably have to move it to the computer to do that so that you can use the arrow keys to move frame by frame through the video to find the time. You could simply use a stopwatch to measure how long it takes to get from the mark to the floor. But how long is that? For mine, it turns out, after doing some unit conversion here, 0.7 seconds to fall. Now, I'd like to do a calculation here. So you might recall we talked about kinematic equations before. So this is one of our kinematic equations. We don't have to go into the details about where that came from, but we find out that the final velocity right before it hits the floor is gravity times time. So we plug in 9.8 meters per second squared, the time that it took to fall to the floor, and I find out that that was 6.9 meters per second. That's pretty good compared to when we used the law of conservation of energy, that the velocity was 6.4. We're only off by 0.5 of a meter per second. Pretty impressive.